So hello student, welcome you all, welcome to this YouTube channel. So today we will discuss LVDT. What is the acronym of LVDT? What is the short form of LVDT? LVDT stands for linear variable differential transformer. LVDT stands for linear variable differential transformer. So it converts displacements into electrical signal. Electrical signal is in form of voltage, right? Voltage V0. So this is the schematic diagram of the linear variable differential transformer. So here we have single primary winding. VP is the primary voltage. Why primary? Because we have connected an alternating voltage source here in this side. That's why this is a primary voltage source. This is a primary winding, right? And here this is the secondary winding, right? Secondary winding consisting of two parts of the windings. So to measure the differential input displacement, we need differential output voltage, and for that we need two secondary winding, right? This is one secondary winding and this is another secondary winding, or you can call it as this is upper secondary winding and this is the lower secondary winding, right? In between primary and secondary winding we have placed a soft iron core here, which is basically movable. It is movable between primary and secondary windings. It is movable. Soft iron core is movable, right? We are providing the displacements to this soft iron core between primary and the secondary windings, right? So in order to measure the input displacements, differential input displacements, we need differential output voltage, and differential output voltage is only obtained when you have two windings in the secondary side, right? So this is upper secondary winding and this is lower secondary winding, right? So now see here, VP is the primary input voltage, supply voltage, that is VP is equal to Vm sin omega t, right? Now the soft iron core, we have placed a soft iron core between primary and the secondary winding. So this core is used to couple the magnetic flux lines of the primary winding with the secondary winding. So wherever this core will be displaced, there you will get the output voltage, right? So for instance, for example, if the core is displaced in the upward position, in that case VB will be 0 ideally, right? So suppose if I am displacing this core in the upper part of this winding, secondary winding, in that case the flux lines from the primary will be linking with the upper part of the secondary winding only, and in such case you will get VB, that is this voltage, that is the lower part of the secondary winding, induced voltage, that is VB, which is in the lower part of the secondary winding, it will be 0 because no flux line is linking with this lower secondary winding, right? So VB will be 0. So here you see that Vp is the primary voltage, it is Vm sin omega t, and Va is K1 Vm sin omega t minus phi, and Vb is K2 Vm sin omega t minus phi. Phi is phase shift, right? So differential output voltage V0 will be equal to Va minus Vb, and this is V0, Va minus Vb. Output voltage V0 is Va minus Vb. So V0 is K1 minus K2 Vm sin omega t minus phi. What is this K1 K2 now? K1 and K2 are basically K1 and K2, they depend on the number of turns on the transformer, on the windings of the transformer, right? If K1 is equal to K2, that means windings are identical, core windings are identical, right? So K1 and K2 depends on the number of turns in the windings of the transformer, right? So if K1 is equal to K2, then we say that the windings are identical, core windings are identical if K1 is equal to K2, right? So V0 is Va minus Vb, so V0 is K1 minus K2 Vm sin omega t minus phi. So if the core is displaced in the upward position, right? If the core is displaced in the upward position, that means if this soft iron core, if it is in the upper part of the secondary winding, that means flux lines now they will be linking with this upper part of the secondary windings only through this soft iron core, right? And only induced voltage Va will be obtained, right? And in that case Vb will be 0, right? So this core is used to couple the magnetic flux lines of the primary winding with the secondary winding. Depending on the displacement provided at the input side, depending on the displacement provided to this core, we will get the differential output voltage in the secondary side. So if the core is displaced in the upward position, in that case you will get only induced voltage V only, right? Because rate of change of the flux is induced voltage, right? So by the principle of induction you will get induced voltage in the secondary winding, right? That's a fundamental transformer action, right? So if the core is displaced in the upward position, then flux lines will be linking with this upper part of the secondary winding with this only. In that case you will get Va only and Vb will be 0, right? Ideally, right? Vb is 0, that means no flux lines are linking from primary to lower part of the secondary winding. So that means Vb, no induced voltage Vb will be there, that's why Vb will be 0. If only very few number of flux lines are linking with the lower part of the secondary winding, then this will be very less. Let us suppose this is 1 volt, right? So ideally if no any flux line is linking with the secondary lower part of the secondary winding, then we will say Vb will be 0, right? In that case Va will be K1 Vm sin omega t minus phi, and V01 will be equal to Va minus Vb, that is K1 Vm sin omega t minus phi, right? Vb is 0, so that means this output voltage is now positive, right? Output voltage is now positive, right? Positive. So you will get this kind of voltage, positive voltage, right? Now suppose if the core is displaced in the downward position, if the core is soft iron core is displaced in the downward position, right? In that case what will happen? If the core is displaced in the downward position, that means if the displacement, if the movement, if it is in the downward position, then flux lines will be linking with this lower part of the secondary winding only, right? Flux lines will be linking with the lower part of the secondary winding. That means the induced voltage only, the induced voltage that is present only is Vb, right? Only Vb will be present, and since no flux lines are linking with the upper part of the secondary winding in this case, so that's why induced voltage VA is 0 ideally, right? So if the core is displaced in the downward position, then VA is equal to 0 because no flux line is linking with this upper part of the secondary winding. So induced voltage VA is 0, right? So only induced voltage in the secondary side is VB. So VB is K2 Vm sin omega t minus phi. So V02 will be equal to VA minus VB. So minus K2 Vm sin omega t minus phi, because VA is 0 in this case. So that's why this voltage is negative, right? So that means this is 180 degree phase shifted. In this case, the output voltage is 180 degree phase shifted. As you see the wave shape is 180 degree phase shifted. Earlier, when the core was displaced in the upward position, then you were getting this kind of voltage. It was positive. But now, since you have displaced the core in the downward position, you will get a output voltage which is negative. That means it is 180 degree phase shifted. So this negative sign means core displacement is now in the opposite direction, right? Core displacement is now in the opposite direction. So this negative sign indicates that displacement is in opposite direction, 180 degree phase shifted. That is the meaning of negative output, right? So here in this case, you will get negative output voltage when the core is displaced in the downward position, right? So likewise, depending on the displacement that you provide to the soft iron core, the differential output voltage will be obtained in the secondary side, and which will be corresponding to the displacement which is provided to this soft iron core, which is placed between primary and secondary, right? So that's how this core, this soft iron core is used to couple the magnetic flux lines of the primary winding with the secondary winding, and depending on the moment of this core, you will get the differential output voltage in the secondary side, which will be corresponding to the input displacement that is provided to the soft iron core, right? So practically, if you see that, if you do the practical in the lab, then suppose you get when you displace the core in the upward position, and you get VA, output voltage VA, suppose it is 10 volt, and suppose you get VB that is very less, that is suppose it is 1 volt, then you will get output voltage V01 is equal to 10 minus 1, VA is 10, VB is 1, so 10 minus 1, that is plus 9 volt, right? And if you displace the core in the downward position, in that case you will see that VA will be very small, right? And only VB will be present, right, majorly. So that's why you will get the output voltage due to the lower part of the secondary winding, so only VB will be present. So that's why you will get phase shifted output, right? So that's how your LVDT will be converting the displacement into electrical signal, right? So since it converts displacement, which is basically non-electrical quantity, to some electrical signal that is in form of voltage here, so that's why this LVDT is basically a transducer, because transducer means the device which converts any non-electrical quantity like pressure, force, flow or displacement into some kind of electrical signal. So that device is basically known as transducer. So that's why LVDT is basically a transducer. LVDT is fundamentally a transducer, right? Because it converts a non-electrical quantity into electrical signal. it converts the displacement, which is non-electrical quantity, into electrical signal, which is in form of voltage here, right? So LVDT means linear variable differential transformer. It converts the linear motion or the input displacement. See here, we are displacing the core linearly. So that's why it is a linear variable differential transformer, right? So it converts the linear motion into electrical signal, or you can say it converts the displacement into electrical signal, right? So here the sensitivity of LVDT, it is given by the ratio of output voltage V0 divided by displacement. So suppose you provide 1 millimeter displacement at the input side. Corresponding to that 1 millimeter, whatever the differential output voltage you will be getting at the output secondary winding, that will be output voltage V0. Suppose you get output voltage 10 volt by the displacement of 1 millimeter. So the sensitivity will be, in this case, will be the 10 volt divided by 1 millimeter. That means 10 volt per millimeter. That is the sensitivity in that particular case, right? Suppose you provide 2 millimeter of displacement, and that 2 millimeter of displacement, suppose you get the some output voltage, right? So you divide that input displacement into the that output voltage that you obtain. So that will be the corresponding sensitivity in that particular case, right? So sensitivity is output voltage V0 divided by displacement that you provide at the input, right, to the soft iron core, right? Soft iron core is always placed between primary winding and the secondary winding. So if you plot a graph between output voltage and displacement, output voltage V0 and displacement, then you get this kind of characteristics, right? This kind of characteristics. So here it is slightly shifted from the origin. That means this shift from the origin is basically due to the residual voltage, right? It is due to the residual voltage. Residual voltage is that voltage that is already present in the winding, right? Because you have performed the experiment and the core will be magnetized, the windings will be magnetized, and due to that some voltage is initially present in that winding. So next time when you perform the experiment, it will there will be some residual voltage, right? So it is slightly shifted above, shifted from the origin. So that means you will get this kind of characteristics, right? So here the displacement is in one particular direction, suppose in positive direction, suppose plus 5 mm, and here this curve you will obtain when the displacement is in the opposite direction. Suppose this is in the opposite direction, so you will get this kind of characteristics, right, in that side. So minus 5 millimeter, this is plus 5 millimeter. So basically this is the curve when you displace the core in one particular direction, and this is the curve that you obtain when you displace the soft iron core in the opposite direction, right? So that's how you will get this kind of characteristics of LVDT, right? Now what are the applications? You see that the LVDT, like I said, it will convert the displacement into electrical signal, that is in form of voltage, right? So it is used for the measurement of displacement, right? LVDT is used for the measurement of displacement. So by using the secondary transducer force, weight, pressure, flow, and all kind of all such kind of non-electrical quantity can be measured by using LVDT, right? For example, using bellows as a primary transducer, we can convert force into displacement. Using bellows or Bourdon tube, we can now convert force into displacement using bellows and Bourdon tube. Now this displacement Later on, this displacement can be converted into electrical signal in form of voltage using LVDT, right? Using LVDT as a secondary transducer, we can convert this displacement into output voltage, that is electrical signal. Using LVDT, we can convert displacement into electrical signal, that is output voltage. So that's how you convert force into displacement using bellows. Now displacement can be converted into output voltage using linear variable differential transformer LVDT into output voltage. Displacement is converted into output voltage using LVDT. So LVDT now it can be used as a secondary transducer, right? Because using primary transducer we are converting force into displacement, and now displacement is converted into output voltage using LVDT, right? So that was our linear variable differential transformer. It is basically a transducer because it converts a non-electrical quantity into electrical signal. It converts the displacement into electrical signal. How it converts, we have explained already, right? So thank you very much. Thanks for watching. So this question has already been asked in your ESE 2014 examination, right? So thank you very much. Thanks for watching. For all such kind of exam oriented videos, please subscribe to this channel. Thank you very much. Thanks for watching.